Hi everyone, welcome to lecture video 2. Our topic for today is optimization. I'd like to start with sort of a motivating question. Our question is, what is the greatest possible product of two numbers whose sum is 9? Now, I could ask this question to a fifth grader, and they would understand the question, and they could maybe try to figure out the answer. So if you were in fifth grade, what might you try to do to answer this question? You might say, well, two numbers whose sum is 9. So what are some options? I could say 0 plus 9, and that gives me, so we'll just make a little column here for product. That gives me 0. I could go 1 plus 8. That gives me 8. 2 plus 7 gives me 14. 3 plus 6 gives me 18. 4 plus 5, 20. 5 plus 4 gives me 20. I think even a fifth grader would be able to realize that we're going to start repeating these numbers just in the reverse order. So we've basically already found all the possible products. And so maybe this is our fifth grader's guess. But this student has no way to prove this. They don't necessarily know that this is the absolute right answer because maybe the answer involves decimals, right? So they're basically just doing some trial and error. But now with calculus, we have the tools to actually find the precise right answer and argue rigorously that our answer is correct. So let's say that our two numbers are x plus y equals 9. The first thing we want to notice is that once we know the first number, say the first number is 2, we know the second number. So in that case, y would be 7. And that's just coming from this basic algebra. We're subtracting x from both sides. So we have that y is 9 minus x. And so that means that our product is x times y, which is x times 9 minus x. And this is what we want to make as large as possible. Now, if we were to just graph this, let's open up Desmos here and go x times 9 minus x. Then we see, so for any x that we input, we see what our product is going to be. And we find actually that the highest the product can be is 20.25 when x is 4.5. Now, how would we find that without graphing? Because that is actually our goal. And so we see actually now that our fifth grader's guess was not quite right. They were close, but not quite right because they didn't think about the possible decimals. So let's go and factor or expand this out. So we have 9x minus x squared. The thing that we want to realize is that when a differentiable function, right, all polynomials are differentiable, which means the derivative exists everywhere. We can kind of think of that as being like there's no points on it, right? It looks smooth. We know that when it reaches its maximum, the derivative is going to be 0, right? There's a horizontal tangent at that line, right? The tangent is going to be the line y equals 20.25. So essentially, in order to find the maximum, we need to set the derivative equal to 0, right? Because the derivative gives us the slope of that tangent line. So let's find the derivative. We're finding d dx of 9x minus x squared, and that equals 9 minus 2x, and we're setting that equal to 0. So let's go add 2x to both sides. We say 9 equals 2x, and x equals 9 over 2. So, and if we wanted to write that without using fractions, we could say x equals 4.5. And now the important thing to do after we solve for x in one of these problems, and this is a mistake that I see a lot, is people, they find their x, they're like, okay, that means that I'm done, right? We're not done because the question doesn't ask you what is x. The question asks what is the greatest possible product of two numbers, right? So we have to remember we found x, but what do we really want? Well, we really want p, which is our product, which we said is x times 9 minus x. So that is 4.5 times 9 minus 4.5. And so that's 4.5 times 4.5, which is 20.25. So that's going to be our final answer. And now, because we used calculus, we are confident that this is actually the correct answer because we found it rigorously rather than just guessing and checking. Our next question is this. Sharon wants to build a rectangular garden against her house with 300 feet of fence. What is the greatest possible area of her garden? So let's think about some possible situations here. So perhaps she wants to make this side 50 feet, which means that this side is also 50 feet since it's a rectangle. So overall, between those two sides, we used 100 feet. So we have 200 feet left of fence. And so we can put that right here. And the area of this garden is 50 feet times 200 feet, which is 10,000 square feet, which we write like feet squared. It's important to use the right units here, and we can always figure out what units we should use, because just imagine that that instead of FT, we had an X there. So what if we said, what is 50X times 200X? Well, we would say that that was 10,000 X squared. Let's do another possibility. So perhaps this side was 100 feet and this side was 100 feet. That would leave another 100 feet for this side. And once again, 100 times 100 is 10,000 square feet. So we should ask, is it possible to make a garden that's bigger than 10,000 square feet? Because this is just guessing and checking. And typically when we do these optimization problems, we don't need to start with guessing and checking. I'm just doing it for these first two problems to help us develop intuition about what exactly these problems mean. One other thing I want to point out about this particular problem is that notice that there's no fence on the top part of the garden because that is the house itself and the house is enclosing the fence. It's enclosing the garden. Let's come up with a way to formalize this problem. Let's call this side X, which means that this side must also be X. And for now, we can call this bottom Y. But we know that we have 300 total feet of fencing, and we want all of these to add up to 300. Now, really quick, I should mention, because maybe you're thinking that, well, maybe the biggest area I can get that by using actually less than 300 total feet of fencing. But that's not true. So suppose you thought that you had maximized the area, but you didn't use all the fence. Well, then I could just stick some extra fence somewhere on this side and basically just stretch the garden out horizontally, and then I have a bigger area. So your area wasn't maximized. So we know that we need to use all of the fencing in order to maximize the area, which means that we do know that 2x plus y equals 300, which means we can solve for y as 300 minus 2x. So now we know that area is, we could call this width times height if we wanted to, which is 300 minus 2x times x, which is 300x minus 2x squared. Now, just like our first problem, we know that area will achieve a maximum when the derivative of area with respect to x is 0. So we're going to calculate dA dx, which is 300 minus 4x, and we're going to set that to 0. So we have 300 equals 4x, or x equals 75. So that says that x was this side is 75 feet. X on this side is 75 feet. So that means that we used 150 feet. And so we have 150 left, so 150 feet, right? Which we could also calculate specifically by using this formula, y equals 300 minus 2x, but that's essentially what we did, right? We said 300 minus that 150 that we already used. So this side is 150 feet. So the area is going to be 75 times 150, which is 11,250 square feet. So we actually did find a bigger area than some of those things we tried before. And if we, again, look at exactly what the problem is asking, it says, what is the greatest possible area? And so our answer is going to be that area. So it is 11,250 square feet. Here's a possible variation of that problem. It says Sharon wants to grow tomatoes, strawberries, and squash, each in its own section, separated by fencing perpendicular to her house. What is the greatest possible area for a garden with this configuration? So what that would look like is this. So notice that now we're using fencing inside of the garden as well. If we set it up as before, we can still call the side X, and that means that all of these pieces of fencing have a length X, and then we have one side with length Y. But now we have 4 times X plus Y equals 300. So Y equals 300 minus 4X, which means that our area equals X times Y, which is X times 300 minus 4X, which is 300X minus 5X squared. And we would proceed with the problem in the same way as before. But since we have a different function for our area, we're going to end up with a different solution. And here's one more possible variation. It says, this time, imagine that the garden is not against her house and that she wants it separated into 2 sections. Find the maximum possible area. So here's our diagram, and we see that now the top is also made a fence. So we'll begin as before. I'm going to label this side X, which means all of these, which have the same length, are all going to be X. Now let's label the bottom Y. And this time, unlike before, since we have fence on the top, we have to label that Y too. So all of the total fence that we're using, we have 3 lengths of X plus 2 lengths of Y. And we know that altogether that equals 300 feet. So we can solve for Y. We have 2Y equals 300 minus 3X, or Y equals 150 minus 3 halves X. So then when we go to find our area, we have area equals X, Y equals X times 150 minus 3 halves X, which is 150X minus 3 halves X squared. And then we'd go ahead as before, taking the derivative of that, setting it equal to 0, and finding the X that maximizes that, and then multiplying that by the Y that we get from that X, which is 150 minus 3X squared. Here's our next question. A rectangle is inscribed with its base on the x-axis and its upper corners on the curve y equals negative x squared. What are the dimensions of such a rectangle with the greatest possible area? So over here we have a diagram of what this looks like. So we have this function y equals negative x squared, and we're basically trying to fit a rectangle underneath of it that has the greatest possible area. And so here is our kind of Desmo simulation of what this might look like. So these are all different rectangles that can be inscribed underneath of this function. And we're trying to find the rectangle that has the biggest possible area. So how are we going to figure that out? So let's see how we want to set this up. Now it's tempting to say, let's take this here and make it X. So for example, if we wanted to make that bottom 2, right, then that would mean that we were going from -1 to 1. Of course, that's not what's drawn here specifically, but that means that this point here is x over 2, and over here is negative x over 2, which means that up here, so our x value is x over 2, and our y value is e to the negative x over 2 squared. And that's kind of ugly. It's not something that I really want to start doing calculus with. So I'm going to do something a little bit different instead. That would be fine, though. We could do it. And if we did it that way, we would get the right answer. So don't be scared that you're setting it up wrong. It's just that certain setups are going to be a little bit cleaner than other setups. So what I think is the cleanest setup here is, instead of naming the length of the bottom of the rectangle X, I'm going to say that the position of the right side of the rectangle is x, so that our rectangle goes from negative x to x, and that causes the length of the bottom to be 2x. But then when I plug x into the function, the value of this function here, which is the same as the height of the rectangle, is going to be just e to the negative x squared. Okay, and so that's just going to work out a little bit nicer for us. So let's go here. Area is width times height, or you can call it length times width, whatever you want to say, is 2x times our height, which is e to the negative x squared. Okay, so let's maximize this. Remember, we want to take the derivative of our function here, and we're going to set that derivative equal to 0. So dA dx, our derivative, equals, okay, now how do we take this derivative? We have a function multiplied by another function, so that means we're going to use product rule. So it's the derivative of the first, so that gives us 2, times the second, so times e to the negative x squared, plus the first, 2x, times the derivative of the second. So the derivative of e to the negative x squared, well, we know that the derivative of e to the something is e to that something, but then we have to move inside because inside we have this negative x squared function, and we have to do chain rule and multiply by that. So derivative of negative x squared is negative 2x, right? So inside of our product rule, we had to do a little bit of chain rule right here. Okay, so let's clean this up a little bit. We have 2e to the negative x squared, and then I can combine those 2's into a negative 4, so minus 4. I have 2 x's, so I have x squared e to the negative x squared. And I'm gonna set that equal to 0. Now let's try to factor anything that I can out of this. So the greatest common factor between these, I see they both have a coefficient that's divisible by 2, and they both have an e to the negative x squared. So I'm going to take out a 2e to the negative x squared. That leaves me, well, I just have to multiply that by 1 to get that first thing, which is 2e to the negative x squared. And then for the second one, I still have a negative 2 left in that coefficient, and I still have an x squared left, and I took out the e to the negative x squared. So we have this equals 0. Now, when I have two factors that equal 0, I know that one of them has to be equal to 0, right? The only way to get 0 from multiplication is if one of those things is 0. So our first option is that 2e to the negative x squared equals 0. I can always divide by a constant, which but I can not always divide by a variable. That's important to know. But I can divide both sides here by 2, and I have e to the negative x squared equals 0. So now we have e to some power equals 0. But remember that e to any positive power is e times itself, some positive number of times, and that's a positive number, right? Because e is a positive number. Or e to a negative number is 1 divided by e to the positive version of that power. So we have 1 divided by some positive number, which is still a positive number, right? So there's no possible way that e to something can be 0. So this, what we wrote on the left side, this is impossible. So there's no x that can make that true. So we're going to say no solutions. So that means that 1 minus 2x, or sorry, 1 minus 2x squared equals 0. So 1 equals 2x squared. Divide both sides by 2. X squared is 1/2, or x equals the square root of 1/2. We can take the square roots of the top and bottom of a fraction individually. That's an important property to know. So that's the square root of 1 over the square root of 2. Square root of 1 is 1, so that's 1 over the square root of 2. And it's a little bit unconventional to have square roots on the bottom, so it's typical to just multiply the top and bottom by the bottom in this case. By definition, root 2 times root 2 is 2, and 1 times root 2 is 2. So we have x is the square root of 2 over 2. And then, so let's see, let's kind of draw a quick sketch of our graph again over here. So that means that this right here is root 2 over 2. So our coordinate of this corner is going to be root 2 over 2 times e to the negative root 2 over 2 squared. And so what is this? This is e to the negative 2 over 4, which is e to the negative 1/2, which means 1 over e to the 1/2, which means 1 over root e. That means that our height is going to be 1 over root e. Let's actually draw a separate rectangle right here. And so our height here is 1 over root e. Now, I know I just said that we shouldn't have radicals in the bottom of a fraction. So I could do the same thing I did before and say that this is root e over e. We still don't have a rational denominator in either case because e isn't rational anyway. And the first one is simpler, so we're going to go with that. So this is 1 over root e. And the bottom, remember, so if this here goes from 0 to root 2 over 2, then that is root 2 over 2. So the length of the whole bottom is root 2 over 2 times 2, which is root 2. And let's just review really quick what this is asking us for. It says, what are the dimensions of such a rectangle with the greatest possible area? So our answer should be the dimensions. And so we can just try to write that neatly as our answer. Dimensions root 2, 1 over root e. And this is going to be unitless because we're just working on our coordinate plane and there's no units on that. Here's our next question. It says, a box with an open top is constructed by cutting squares out of the corners of a 6-inch by 10-inch piece of paper. What is the greatest volume that can be achieved for a box constructed in this way? Okay, I just want to stop screen sharing for a second so you guys can see what we mean here exactly with this problem. So here's our piece of paper. Let's say this top side is 10 inches, like we said, and this side is 6 inches. And then we cut out these squares in the corner. And so what we're going to do, right, is we're going to fold up all of these new flaps that we created to make a box like this, right? Now, if we say that each of these sides has a length of x, let's think about what that means for our box. So when I fold this up like this length right here of the box, the side that's facing you, was, so the whole length from here to here was 10 inches, right? And we took x away here and we took x away here. So now what's left is 10 minus 2x for that length, right? And same thing over here. The whole side of this piece of paper before I cut it was 6, and then we took x away from both sides, and so the length of the bottom of this flap, which is this side of the box, is going to be 6 minus 2x inches. And then the height of the box, right, however long the flap is right here, that's how tall the box becomes when I fold these up. So the height of the box is going to be x inches tall, right? So overall, the volume of this box is 10 minus 2x times 6 minus 2x times x. We have a diagram here, which is the flattened out version of the box, like we just saw. So if we do what we just explained, and we label x to be this length of this small side here, which means that what's left over after we take 2 x's out of the 6 inches is 6 minus 2x. And similarly, for the bottom here, we have 10 minus 2x. So as we just saw, we have volume equals length times width times height, and we just saw how our length is 10 minus 2x, our width is 6 minus 2x, and our height is x. I'm going to start by multiplying this part through. So I have 10 minus 2x times 6x minus 2x squared. And then let's just FOIL this out. So 10 times 6x is 60x. 10 times negative 2x squared is minus 20x squared. Negative 2x times 6x is negative 12x squared. And negative 2x times negative 2x squared is positive 4x cubed. Let's rewrite this in a more conventional order. So we have a equals 4x cubed minus 32x squared plus 60x. Now, as usual, we're going to take the derivative of the area with respect to x. And so we have dA dx equals 12x squared minus 64x plus 60. Make sure you understand where I got all of these from, right? For this first term, I took this 3, I pulled it out in front. We have 3 times 4 equals 12, and then we decreased the power, and we did the same thing for the rest of them. And we want to set that derivative equal to 0. The first thing we can do to make this a little bit simpler is we can divide both sides by 4. So we're going to get 3x squared minus 16x plus 15 equals 0. Now we will notice that this left side is not factorable. So we do need to use either completing the square or the quadratic equation. I'm going to choose to use the quadratic equation. So we have x equals, let's write out the formula really quick. So that's going to be negative 16. So that's positive 16. Remember, a is our coefficient here, b is our coefficient here, and c is our coefficient here. It's not really a coefficient, but it's the coefficient of 1. So we have 16 plus or minus the square root of negative 16 squared minus 4 times 3 times 15 divided by 2 times 3. So that's 16 plus or minus the square root of 256 minus 180 over 6, which is 16 plus or minus the square root of 74 over 6. And 74 is 4 times 19. So we can write that like this. The square root of 4 times the square root of 19 over 6. And the square root of 4 is 2. So we have 16 plus or minus 2 root 19 over 6. And then I can divide the top and bottom by 2 to get 8 plus or minus root 19 over 3. So we notice now that we actually have 2 solutions. We have 8 plus the square root of 19 and 8 minus the square root of 19 over 3. So how is that possible, and what does that mean? Here we have the graph of x times 10 minus 2x times 6 minus 2x squared. So the value of this graph gives us the volume of our box for a particular side length of the square that we removed. That means, for example, that if we removed a square of side length 2, the volume of our box would be 24. Now we see that there are 2 points on our graph that have horizontal tangents. One of them is x equals 8 plus 19 divided by 3, and the other is x equals 8 minus 19 divided by 3. And so the one that maximizes our function is 8 minus 19 divided by 3. If we have 8 plus 19 divided by 3, then when we compute 6 minus 2x, that actually ends up being a negative number. So the volume doesn't make sense at all, right? We should note that x can't possibly be bigger than 3, or else the question doesn't make sense. We can't remove an x so large that our squares combined are larger than the paper. In practice, what you would have to do here, if you didn't have access to graphing software, is you would plug 8 plus root 19 over 3 and 8 minus root 19 over 3 into your original equation for volume and find which one gives you the maximum value. Another approach would be to take the second derivative and plug each of those roots into the second derivative and find the one where the second derivative is a negative. Because if we think about our graph here, the maximum occurs when the function is concave down, and the minimum occurs when the function is concave up. So in order for the root to represent a maximum, the function has to be concave down, which means that the second derivative has to be negative. Since our numbers here are so gross, and I'm not going to give you a question that is this tedious to work out on your midterm, so you don't have to worry about this. We're just going to kind of black box this section and say plug 8 plus root 19 over 3 and 8 minus root 19 over 3 into x 10 minus 2x times 6 minus 2x. And as we saw, 8 minus 19 over 3 gives us the larger result. And if we go and look back at what the problem asks us, it says, what is the greatest volume that can be achieved for a box constructed in this way? So the maximum volume is going to be what happens when we plug that number into our volume formula. So it's going to be 8 minus root 19 over 3 times 10 minus 2 times 8 minus root 19 over 3 times 6 minus 2 times 8 minus root 19 over 3. And you wouldn't need to expand this on an exam. And like I said, you're not going to get this tedious of a question on this exam, though you could get a question of this type with a box, but I will make the numbers work out better than this question. There are certain things that you're expected to simplify, but this isn't one of them, and those details will be on the instructions of your exam. So essentially, this is our final answer. All right, here's our next problem, and I promise the numbers for this one will work out a lot better than the last one. So it says we want to build a box with an open top and a base whose length is twice its width. We will build the base from titanium, which costs $6 per square inch, and the walls from copper, which costs $3 per square inch. With a budget of $144, what is the largest possible such box we can construct? So I've tried my best to draw a box over here, and we said that the length is twice the width. So let's make the width be called x, and that means that the length here is 2x. And we have a height as well, and it's not instantly clear what that height is going to be in terms of x. So let's think about what we did in the last problems when we had a variable that we didn't know. When we had, for example, our garden, we had an x and a y, and we figured out what the y was going to be based on some restraint. So for example, our restraint in the garden problem was the total amount of fence that we have. In this case, the restraint that we have is our budget. So we have a $144 budget, and that's how we're going to figure out what h is in terms of x. Because remember, we need to have everything in terms of just one variable so that we're able to take the derivative. So let's work on this one bit at a time. Let's first figure out the area of the base. The area of the base is our length times our width, which is x times 2x, which is 2x squared. Let's figure out what the area of the front is going to be. That's going to be length times height, which in this case is 2xh. And the area of the side, meaning the left side or the right side, is going to be, right, we're talking about this side right here. That's going to be x times h, or well, it's our width times our height, which, as we said, is x times h. So now let's figure out the total surface area of the sides of the box. So surface area of all sides. So we have two sides that look like the front. So 2 times 2xh. And then we have two sides that look like the left or the right. So 2 times xh. So that is 4xh plus 2xh. So that is 6xh. So now we have figured out the area of the base. And so all of this area here is made of titanium, and all of this area for the sides is made of copper. So let's figure out the total cost of our cube, or not cube, but of our box. So the base has an area of 2x squared, and each square inch for the base costs $6. So it's going to be 6 times 2x squared plus 3 times 6xh. And we know that the cost is going to be $144 because that's our budget. So if we simplify this a little bit, we have 12x squared plus 18xh equals 144. So we're going to get 18xh equals 144 minus 12x squared. Remember that we're trying to isolate h, so that's why we're doing it this way. And then we're going to divide both sides by 18x. So we get h equals 144 minus 12x squared divided by 18x. We could divide the top and bottom by 6, though, if we wanted. So 144 divided by 6 is 24, minus 12 divided by 6 gives us 2x squared over 18 divided by 6 gives us 3x. It's not strictly necessary. It will just make our calculations a little bit easier moving forward. So now let's figure out what we're trying to maximize. And so that is our volume. Volume is length times width times height. And so that's 2x, that's our length, times x, that's our width, times 24 minus 2x squared over 3x, that's our height. And we can cancel a little bit to make this simpler since we have an x in over here, right? Anything that's not in the denominator is essentially in the numerator. So we can cancel that out with this x in the bottom. And so we have that our volume is, and I'm gonna pull that 1/3 out in the front so that we can avoid working with a big fraction. So it's 2x times 24 minus 2x squared. And so that's 1/3 times 48x minus 4x cubed. So now we want to take the derivative of this. So that's going to be 1/3. It's just a constant being multiplied, so we can keep that out front, times 48 minus, pull that 3 down. We're going to get 12x squared. Actually, let's definitely not say equals right there. We want to say that dv dx equals this. And that's what we're going to set equal to 0. So now I can actually distribute this 1/3 through there, and I get 16 minus 4x squared equals 0. So 16 equals 4x squared. I'm going to divide both sides by 4, so I get x squared equals 4, or x equals plus or minus 2. But if we think about what x represents, we know that x has to be bigger than 0, right? X is one of the side lengths of the base. So x has to be positive, and that means that x equals positive 2. Okay, so now we found the x that maximizes our volume. So if we go and try to draw our box again, we know that this side is 2, right? X is 2. This side was 2x, so that's going to be 4. And then our height had a little bit more complicated formula for it. So we're going to go, we have h equals, and let's pull this back down from above. So our h was 24 minus 2x squared over 3x. So that's going to be 24 minus 2 times x squared. So that's 2 times 4, which is 8 over 3 times x. So that's 6. So 24 minus 8 gives us 16 over 6, which is 8 over 3. So ultimately, let's just kind of redraw our box one last time. We've got a height of 8/3, a length of 4, a width of 2, and we want to make sure that we have units on all of these. And that means that our volume is going to be 2 inches times 4 inches times 8/3 inches, which is 64/3 inches cubed. And a question like this could ask you for this max volume, or it might ask you for these dimensions. In this problem, we didn't specify just so we could figure all of these things out and show you all of the possible things that you might need to find in a question like this. Here's our next problem. It says, we want to build a box with an open top and a base whose length is twice its width. We will build the base from titanium, which costs $6 an inch squared, and the walls from copper, which costs $3 per inch squared. If the box must have a volume of 64/3 inches cubed, what is the cheapest such box? Now, this should look incredibly familiar because the conditions that we started with are essentially the same as the last problem. The difference is that the last problem, we said, we're going to pay this much money. Let's make the box as big as possible. And this time we're saying the box needs to be a certain size. How can I do it as cheaply as possible? But we notice that our diagram is going to be the same, right? We have this same condition that the length is twice the width of the base, and we have the same prices. So everything that we have up here, the area of the base, the area of the front, the area of the side, the surface area of all the sides, and the formula for the cost of the box is all going to be the same. So I'm actually just going to copy this and paste that right back down on our new problem here. The only difference is this time we don't know what the cost is going to be. Instead of fixing the cost, we are trying to minimize the cost. Now, this is the first problem where we are minimizing something instead of maximizing something. But if we think about what a graph is going to look like, as long as the function is differentiable, the minimum and the maximum will both have a derivative of 0, right? The horizontal tangent will be 0 at the top of a slope or the bottom of a valley. So now that we have our cost function here, we want to take the derivative of it, but we can't do that because we have an h here. So we need to have it all in terms of one variable. Now, how are we going to do that? Before we used the cost function to solve for h because we had a fixed cost, but this time we have a fixed volume. And so that's what we're going to use to solve for h this time. So we have 2x times x times h equals 64 thirds. So we have 2x squared h equals 64 thirds. And then we're going to divide both sides by 2x squared. So we have h equals 64 over 3 times 2x squared. And then I can cancel what 2 out from the top and bottom. So we get 32 over 3x squared. Now I'm going to plug that h into our cost function here. And so we're going to get 12x squared plus 18x times 32 over 3x squared. Now let's simplify this a little bit. So now we have 12x squared plus 6 times 32 over x, which is 12x squared plus 192 over x. And so that's our cost function. So let's actually write that over here. Let's use a variable c to represent our cost. And now we've got our cost written in terms of just one variable, which is exactly what we want because that allows us to take the derivative of our cost in order to figure out where it has a horizontal tangent, which would be the minimum or the maximum. But in this case, we're looking for the minimum. So let's set dc over dx. And that's going to be 24x plus, and let's think about how we take the derivative of this. For some people, it's helpful to rewrite fractions like this with a negative exponent or negative power. So this gives us 192x to the negative 1. And so then we can think about bringing that negative 1 out in front and then reducing the power by 1. So we get negative 1 times 192 times x to the negative 2. So we get 24x minus 192x to the minus 2. Now let's just take a quick little excursion. And I want you guys to think about how we actually factor the greatest common factor out of a polynomial. So if I said, okay, I have 12x to the 6th plus 16x to the 4th plus 4x cubed. How do we figure out what power of x I'm going to pull out front? Well, I'm going to look at all of the x's that I have here, and I'm going to see which one of them is raised to the lowest power, right? So that means that I can pull an x cubed out of that. It also happens that I can pull a 4 out of that in terms of the coefficients. And so that's going to give me 3x cubed plus 4x plus 1, right? So for each of these new x's, I subtracted 3 from the power because that's what I pulled out front. And the reason I'm showing you guys that is because we're going to set this derivative to 0, and we need to use this rule in order to factor it. but for some people, it seems a little bit less intuitive when we have a negative in the exponent. So we have 24x to the first minus 192x to the minus 2 equals 0. So we're going to look at these x's and see which one is raised to the lowest power. Well, minus 2, right? Minus 2 is less than 1. So that's what we're going to pull out in front. And I could also pull out the GCD of the coefficients, but it doesn't really matter. So now how do I figure out what the new power for my x after my 24 is going to be? Well, that's going to be 1 minus negative 2. So that gives me x cubed, right? 1 minus negative 2 is 1 plus 2, which is 3. And we can double check that makes sense by looking and distributing that negative 2 back through, and we see that that would give us back that x that we originally had. So that makes sense. And then we're going to go minus 192, right? And that x goes away. Negative 2 minus negative 2 is 0, and x to the 0 is 1. And so that's what we're going to set equal to 0. And now we have two separate factors here that we want to set to 0. So we could say x to the minus 2 equals 0. But that's saying that 1 over x squared equals 0. Now, is this possible? Could we ever have a fraction with 1 in the numerator be equal to 0? No, right? Not unless the denominator was infinity, but infinity isn't a number, so that's not a solution, and so there's no solutions here, right? The only way that a fraction can be equal to 0 is if the numerator is 0, and it isn't, and it can't be because it's just a constant. So that leaves us with the other factor here, and so that is 24x cubed minus 192 equals 0. So 24x cubed equals 192. Let's divide both sides by 24. We're going to get x cubed equals 8, right? 192 over 24 is 8. And then we're going to take the cube root of each side. So what do I multiply by itself 3 times to get 8? And that is going to be 2, right? 2 times 2 times 2 is 8. So x equals 2. Notice that when we have odd powers, we don't have plus or minus 2 because negative 2 times negative 2 times negative 2 is negative 8. So the only solution here is x equals 2. And now we can go back and plug this in. So if we remind ourselves what the problem says, it says, what is the cheapest such box? So we said the cost of the box we figured out was 12x squared plus 192 over x. So cost is 12x squared plus 192 over x. So that is 12 times 2 squared plus 192 over x. So that's 12 times 4 plus, actually let's make this x a 2, because that's what x is, plus 96, which is 48, plus 96, and that equals 144. And remember that our units on this is in dollars. And so let's just write that as our final answer, that the cheapest such box is $144. And that, of course, is the budget in the previous problem, which gave us a maximum volume of 64 thirds cubic inches. And now we're fixing the volume and we get that as the cheapest cost. So that is not a coincidence, actually. Here's the last minimization problem we're going to do today. It says, find the point on the line 1/2 x plus 4, which is closest to the point 1, 7. And over here we have a Desmos graph showing that line and that point. If we look at any point on this line, we can draw a line between 1, 7 and the point on our line. And the length of that line is the distance between these 2 points. We can also think of that distance as being the hypotenuse of the right triangle drawn like this. So let's say we have some point xy on the line y equals 1/2 x plus 4. Well, in this case, since it's on this line, we know that y equals 1/2 x plus 4. So we're just going to say that our point is x, 1/2 x plus 4. And now we want to find the distance between our point and the point 1, 7. Let's label our point on the graph here as x, 1/2 x plus 4. That's this point. And then how are we going to find the distance of the bottom of this triangle, the length of the bottom of the triangle? Well, it's the distance between the x coordinate of my point on the bottom and the x coordinate of my point on the top. So the bottom of this is going to be 1 minus x, and this height goes between, it starts at the y value of 1/2 x plus 4, and it goes up to 7. So the height is going to be 7 minus 1/2 x plus 4 inside of parentheses like that. So that's 7 minus 1/2 x minus 4, which I can simplify into 3 minus 1/2 x. And now we're going to use the Pythagorean theorem to find the length of this hypotenuse. And let's write this somewhere else so we have a little bit more space. So we're going to say that d for distance, d squared equals 1 minus x squared plus 3 minus 1/2 x squared. And we can take the square root of both sides. So we get d equals the square root of 1 minus x squared plus 3 minus 1/2 x squared. And I'm actually going to make this d capital just because of the derivative notation. Okay, so now this is the distance. This is the thing that we want to make as small as possible. So we're going to take the derivative of this with respect to x and set that equal to 0. So it's dd dx equals, once again, maybe we should rewrite this a little bit, because remember that a square root is the same as a 1/2 power. So we're going to think about, okay, we'll pull that 1/2 out in front. And for now, we're just going to repeat everything that's inside, and we're going to reduce the power by 1. So 1/2 minus 1 is negative 1/2. But since we had something inside other than just an x, we then have to take the derivative of the inside. So let's think about, what is the derivative of 1 minus x squared? Well, the derivative of something squared is 2 times that something. And then the derivative of 1 minus x, doing chain rule again in here, is minus 1. Okay. And then 3 minus 1/2 x squared, so that's 2 times 3 minus 1/2 x. And then chain rule again times the derivative of 3 minus 1/2 x times negative 1/2. And so that is our derivative, which we have to set equal to 0. Essentially, we have 2 factors here. And this first factor looks like this, right? This first factor has a negative power. So it looks like 1 over 2 times the square root of 1 minus x squared plus 3 minus 1/2 x squared equals 0. And just like we saw before, this is a fraction with 1 in the numerator. There's no way it's going to equal 0. So we have no solutions over here. This side is going to be more interesting, and we're going to clean this up a little bit. This should clean up pretty nice, actually. So let's first just multiply those constants. So I have a negative 2 multiplying the 2 before by the negative 1 after, 1 minus x plus, and then let's multiply this 2 by the negative 1/2. So that actually gives us a negative 1, right? Because this 2 is going to cancel with this, times 3 minus 1/2 x equals 0. Let's distribute through here. So we have negative 2 plus 2x minus 3 plus 1/2 x equals 0. So now we can combine our terms. I'm going to think of 2 as being, well, actually, let's just rewrite this one more time. So 2 is the same as 4 halves. So now I'm going to combine my x terms. I have 5 halves x minus 5 equals 0. So 5 halves x equals 5. And that means that x equals 5 times, just to clarify what I'm doing here, I'm multiplying both sides by 2/5, right? So that all of this is going to cancel out. I have x on the other side, and this is going to be 2/5 on this side, and that 5 is going to cancel out there. So we have x equals 2. Now, once again, we don't finish just because we found x. We have to go look at what the question is actually asking. It says find the point on the line which is closest to the 0.17. So the points on this line are coordinate pairs x comma y, where y is 1/2 x plus 4. So we have y equals 1/2 x plus 4, which is 1/2 times 2 plus 4. So that's 1 plus 4, which is 5. And so we can say the point on the line 1/2 x plus 4, which is closest to the point 1 comma 7, is 2 comma 5. And so that's going to be our final answer. Now, there are tons of optimization problems we could come up with, and you're going to see some optimization problems on your web work that might look a little bit different than the ones we've done. Some might look similar to the ones we've done, but we want to just come up with some general processes so that you're able to come up with these solutions on your own, even for optimization problems that are a little bit different from the ones that we did today. So the first thing we want to do is come up with the equation for what we want to maximize or minimize, right? So I'm actually going to say optimize for what we want to optimize. Step 2 is going to be to identify our constraints. And we're going to use the restraints to solve for all of the other variables in our optimization equation. Then our third step is going to be rewrite our optimization equation in terms of one variable. Our step 4 is going to be to take the derivative of our optimization equation and set it equal to 0. Step 5 is going to be solve for our variable. And then remember that that doesn't mean we're done, because we have one more step, and that is step 6, which is to use the variable to find what the problem is asking for. So that's our general process, and you should refer to this when you're solving the questions on the web work. Of course, come to my office hours if you have any questions on that. And that's going to be the end of our lecture today, and I will see you next time in our lecture on antiderivatives.